Hello and welcome back to MathandBolt. So in today's lecture, we begin with where we left off in the previous one. So we were able to derive an expression for the velocity vector as well as the acceleration vector. So an expression for velocity vector gave us v vector is equals to r dot r cap plus r theta dot theta cap. So the r dot and the theta dot are usually the time derivatives of the respective variables. That means r dot will be simply the time derivative of the distance r, and theta dot is the time derivative of the angle theta. Then we also obtained the expression for the acceleration. So acceleration gave us r double dot minus r theta dot squared. So this was the radial part, so that's r cap plus 2r dot theta dot plus r theta double dot, and this is the angular part. So that means we can now write it as v of r. So vr, that simply means the radial part of the velocity, so that was r dot, and the angular part v theta is equals to r theta dot. Then for the acceleration, the radial part ar is given by r double dot minus r theta dot squared, and the angular part a theta, that's equals to 2 r dot theta dot plus r theta double dot. So now that you have the radial and angular part of both the velocity and the acceleration, let's try to understand the meaning of these components or the meaning of these values with the help of a very simple example. So we consider the case of a circular motion. So what we'll do, we will consider a particle that's moving with respect to a fixed point O, which is at a distance of r. This particle is moving in a circular path. Then what we can say, that since it is moving in a circular path, the radius, the distance r, is fixed. Since it is fixed, so that immediately follows that dr over dt will be equals to 0 and the higher derivatives as well. So d square r over dt squared, so that will be also equals to 0. So that means the radial part of the velocity v of r, which is r dot, so that's the time derivative of r, so that will be 0. Then we have v theta, so v theta will be r theta dot. Then coming to the acceleration, so we have the radial part, so the radial part ar will be, so we have r double dot, so that will be 0. We are left with negative r theta dot squared. And the angular part of acceleration a theta will be, so we have 2 r dot, so r dot is a 0, so we're left with r theta double dot. Now let's say, suppose that r theta dot, which is the rate of change of angle theta, if this is given by omega, then we have v of theta, so that will be equals to r omega, so this is the angular velocity, and we have a's of r, so that will be r omega square, and a's of theta will be r omega dot. So that means the new expression for the velocity will be, so since we do not have any r component of velocity, so that will be 0, no radial part, so we are only left with the angular part, so that's r omega, and that's it, r omega theta. For acceleration, we'll have minus omega square r, so this is the radial part, that's why we are multiplying with the unit vector r cap, plus the angular part, so that will be r omega dot, so this is theta cap. So we have an expression for velocity and acceleration. So here we see that in acceleration we have this radial part, which suggests that our particle also have a acceleration in the radial direction, which is outwards, and this is actually referred to as the centrifugal acceleration, which is always outwards. and we have the angular part, which is r omega dot, so that will be tangential to the path at that particular point, and we have a velocity that is along the tangential direction or the angular direction, meaning only v of theta is present. For the velocity, there is no radial part. So we can infer from here that the velocity has an angular part. That is because our particle is moving along a circular trajectory. So it's evident that it's going to have a velocity along the angular direction. Because of this particular velocity, there is also going to be an acceleration in the angular direction. So that will be r omega naught. Now we see that there is also an extra term, which is the acceleration along the radial directions, which is minus omega square r, and this particular acceleration is going to restrict the motion of the particle along a circular trajectory. So this was a very simple example that helped us understand about the different components of the velocity vector as well as the acceleration vector. Now coming back to the original equation, let us consider a fixed position O. This could be the center of any coordinate frame. Then we have a particle, let's say at point A, and this particle, let's say it's moving along some path. Now let's say a particle which is at point A is at a distance of r from this fixed point O, and also it's directed along OA direction. So this particle, as it is moving along this trajectory, it's going to have some kind of velocity v vector. Now what we can do is we can resolve this vector into its corresponding components. So we have one vector which is along r cap. So this is the radial part of velocity v of r. So let's call it v of r cap. So this is along the radial part r cap in the radial direction. Then we have another one which is r v theta. So this is the angular part of velocity, and this will be along theta cap direction. Fine. Now what we can do at point A, at point O, the angular momentum L vector will be L vector is equals to the radius vector crossed with the momentum of the particle at that point A. So this is how we can define the angular momentum. So we know that the p vector is given as mass times the velocity vector. Since mass is a constant, so we can write it as m times r vector cross v vector. Mass is a constant in the sense that we are only concerned about a constant mass system. Here we are not dealing with the system with variable mass. That's why I'm keeping it as a constant and pull it out. So we have r cross v. Now we have to take care of this cross product r cross v vector. So we obtained in our derivation what was v vector. The v vector is given by r dot r cap plus r theta dot theta cap. We're considering the general expression for velocity vector, not the special case where we consider the circular path, because this is not exactly a circular motion. It's a very different case, general case we'll say. So let's plug in the value of v vector here. So that will be m times, so we have r vector crossed with v vector. So v vector is r dot r cap plus r theta dot theta cap. So upon multiplication we should get, so r dot, so this is a constant, so we have r dot multiply to r vector cross r cap plus we have r theta dot, so that's a constant, and we have r vector cross theta cap. Fine. Now r vector cross r dot, so this will be 0 because they are both r vector and r cap points in the same direction, and since they're pointing in the same direction using the definition of cross product, so this will be equals to 0. So we are left with m, so this entire thing is 0, so r dot times 0 will be 0, plus r theta dot. Now we have r vector, so r vector can be also written as magnitude of vector r, which is simply r times the unit vector along r vector crossed with theta cap. So that gives us m r square theta dot multiplied to r cap cross theta cap. So this is the expression for the angular momentum L vector, and if we consider the magnitude, so the magnitude will be m r square theta dot. So this is the expression for the angular momentum of the particle which is moving along this particular path. Now why we have derived the form for angular momentum will become evident right away. So if we consider the angular part of acceleration a theta, so a theta came out to be 2r dot theta dot plus r theta double dot. Now what to do, this expression can be written as 1 over r multiplied to the time derivative of r square theta dot, meaning if we take the derivative of r square theta dot, and whatever we obtain we divide it by r divided with r, this is going to give back 2r dot theta dot plus r theta double dot. Now we're going to multiply and divide with the constant mass m, so we have 1 over mr times d over dt d of m r square theta dot. Now this is what, this is the expression for the angular momentum, the absolute value of the angular momentum or the scalar angular momentum. So that means we can say that a theta is equals to 1 over m times r times d dt of the angular momentum L. So now we have obtained an expression for the angular part of acceleration written in terms of the angular momentum L. Fine. Now since our topic of concern here is central forces, and we talked about in the previous lecture about central forces. Now what defines a particular force to be central force? First of all, we need to have a fixed center and the force on that particle of some mass m. Now what is it? That force should be either pointing towards the point O or it should be pointing away from that point O. So this is the first criterion. The second criterion was that the force which is acting on that particle m, that force should be purely a function of r. So that means this is f of r times r cap. So this is the second criterion for a force applied on an object of mass m to be categorized as central force. Now we'll use this definition. So we have L vector, which is the angular vector, so that's given by r vector cross p vector. We've already talked about it. Now let's take the time derivative on both sides. So we have dl vector over dt, and that is equals to time derivative of r vector cross p vector, which is equals to, so we have ddt of r vector, so we expanded by using the product rule, crossed with p vector plus r vector crossed with dp vector over dt. So dr vector over dt, that's simply the velocity vector v vector, cross p vector, we use the definition, so that will be m v vector plus r vector crossed with rate of change of momentum, so this is our force vector f of which is a function of r vector. Right? So m times, m is a constant, v vector cross v vector plus r vector crossed with f vector r, which we have said that this is a function of r times r cap. Now here we see that v vector was cross v vector, this is going to be equals to 0 because that means the velocity is in the same direction, plus f of r times, so here we have r vector crossed with the unit vector r cap, which is also going to give us 0. That is because r vector and r cap are both pointing in the same direction. So what we have obtained here is that the rate of change of momentum vector, angular momentum vector, L vector, is 0, which is arising as a consequence of our force being central in nature. And when the derivative of a particular function is 0, that means that L vector is a constant. So this is constant, and when I say it's constant, L vector being a vector quantity, so its magnitude including the direction both are fixed whenever we are working with central force fields. So let's write it down. So what we have obtained here is that the rate of change of angular momentum is 0. What's that? The angular momentum of a particle moving under the influence of a central force is constant or conserved. One can say or conserved. So this is the law of conservation of angular momentum. So coming back to our expression for the angular component of acceleration, we obtained that this is 1 over mr times rate of change of angular momentum. So if we use this result, so here angular momentum L, this is the scalar quantity. Nonetheless, so we say that the angular momentum, the rate of change of angular momentum is 0. So that means the angular part of acceleration is also 0. So that means the particle which is moving under the influence of a central force is not going to get accelerated in the theta direction. So there will be only acceleration along the radial direction, and that will be the centrifugal acceleration, right? So this is one. And also L vector is a constant. I've already mentioned it. Let's write it down. L vector is a constant. This implies that the direction of L vector is also fixed. It's constant. Now if this is constant, then what does it mean? Because by definition we know that L vector, that's given by r vector cross p vector, or which is simply m times r vector cross b vector, and we have already derived this. So we obtained this was equals to m r square theta dot, so we had r cap cross theta cap. This cross product of r cap with theta cap tells us that both lie on a planar surface. That's because the result is the vector L vector, the angular momentum, and this vector is always going to be perpendicular to both r vector and theta vector. And since L vector is a conserved quantity, that means that is constant, whose direction as magnitude both are constant, so it's only becomes possible if we consider that r cap, the cross product of r cap and theta cap, is occurring on a single planar surface. Now let's try to obtain the equation of motion. So from Newton's second law of motion, we know that mass times acceleration, so that's equals to the force acting on the particle, which is a function of distance r. Fine. So that means we have m a vector is equals to the force expression will be f, which is a function of r, times r cap. Now let's substitute a value of acceleration on the left hand side. So for acceleration we have, so if we compare both sides, then we will obtain m times r double dot minus r theta dot squared. So this is the component of r cap, so that will be equals to f of r. So this is equation number 1, and then we have 2r dot theta dot plus r theta double dot is equals to 0. So that means the angular part of acceleration is equals to 0. This is, we have already talked about this. I mean, this is what we just proved a few moments ago. That means in the case of a central force, the angular momentum is always conserved. Thereby, there will be no angular part of acceleration. task will be to solve this differential equation. So let's try to rewrite this equation. So this equation will be r double dot minus r theta dot square is equals to 1 over m times f of r. This is a second order differential equation. So we begin by talking about the total energy of the system. The total energy of the system is E, which is given by the sum of kinetic energy and the potential energy. And let's say that this value is constant. The sum total of all the energy, and the T plus V is a constant. Now what is T? So T is the kinetic energy given by half mv squared, and V is something which is a function of R, and that V of R is actually given by moving a particle from infinity to a point R, which is like force times dr vector. This is the definition of the potential function. Now we need to find out V squared. So V squared will be, let me write it out somewhere. So we had velocity vector. So the expression for velocity vector was r dot r cap plus r theta dot theta cap. So if we take the magnitude of velocity, so that's square root of r dot square plus r square theta dot squared. So that means if we want V square, so that will be simply r dot square plus r square theta dot square. So let's substitute it here. So we have half m times V squared. So V squared will be r dot square plus r square theta dot square plus the potential function V of R. So this is equals to E. Now what we'll try to do, we will use this expression and try to write the equation in terms of R dot. So let me write down the result straight away. That is a very simple algebraic manipulation. So we will get R dot squared. So that will be equals to 2E over M minus 2 V of R divided by M minus R square theta dot squared. So if we take 2 over m as the common factor, so we have E minus V of R minus we have m times r square theta dot squared whole divided by 2. Fine. Now for this term, we are going to do is, let's rewrite this term. So this will be equals to 2 over m multiplied to E minus V as a function of R minus, so we're going to multiply the numerator and denominator by m. So we have m squared in the numerator, so 2m. We are also going to multiply to the both numerator in our numerator with r square. So we have r raised to the power of 4. So r square in the denominator times theta dot square. Why we have done this? Because we know that L, the angular momentum, is given by mr square theta dot. So that means our numerator will become 2 over m E minus V, so function of R, minus L square divided by 2m R squared. So this is R dot squared. So that means if we take the square root on both sides, or you have square root of 2 over m, and this multiplied to this expression whole raised to the power of half. So this will be R dot. In the similar fashion, we can obtain an expression for theta dot. Now what we will need to do is, like, we need to integrate both the two equations, and that will give us the value as a function of time. So we'll be picking this up in the next class, because solving this differential equation is extremely complicated. So what we will do, so we'll find some other ways to find some easier ways to find solutions of RT and theta t. So see you in the next class. Thank you.